Excuse me, sir. What are you doing?
I'll tell you what I'm doing. I want to buy 8 hot dogs and 8 hot dog buns to go with them. But no one sells 8 hot dog buns. They only sell 12 hot dog buns. So I end up paying for 4 buns I don't need. So I am removing the superfluous buns.
I'm sorry, sir, but you're gonna have to pay for all 12 buns. They're not marked individually.
Yeah. You want to know why? Because some big shot over at the Wiener Company got together with some big shot over at the Bun Company and decided to rip off the American public. Because they think the American public is a bunch of trusting nitwits who'll pay for things they don't need rather than make us stink. Well, they're not ripping off this nitwit anymore because I'm not paying for one more thing I don't need. George Banks is saying no.
Limiting reagents, that's today's topic. Now, in chemistry, limiting reagents are going to be a calculation kind of thing. In real life, the idea of a limiting, maybe not a reagent, but a limiting substance is something that we typically take care of in our heads. And for example, I've got here, it's a problem with hot dogs. In order to get them to work out in perfect amounts, you kind of have to do some juggling around or throw away a few buns maybe. But let's go back to our sandwiches, because sandwiches are something we can visualize a little bit better. So my sandwich recipe this time is 2 breads, 1 cheese. Put those together, you make 1 sandwich. Now again, keep in mind that to make a sandwich here I need 2 breads, but I'm only going to be making 1 sandwich. Okay, just in terms of keeping the numbers straight. So we do all this stuff in our head, but let me ask you a question. How many sandwiches could I make from 20 pieces of bread? Right? You've got your answer. Keep track of that. 15 cheeses. All right, so ignore the breads for a minute. How many sandwiches could I make with 15 cheese? Okay, got your answer. Excellent. Now put it together. What if I had 20 slices of bread, and 15 slices of cheese? How many sandwiches could I make then? Hopefully, your final answer is 10. And the reason it's 10 and not 35 and not 20 and not 15, but the reason it's 10 is that the bread allows you to make 10 sandwiches. The cheese allows you to make up to 15, but I can make fewer sandwiches from the bread. So the bread is then the limiting ingredient, if you will. So the number of sandwiches is limited by the ingredient that runs out first. Let's take that exact thinking and move it into chemistry. So we're going to start with a chemical reaction. Now I picked a chemical reaction that is going to be kind of similar. Remember we had 2 breads and 1 cheese? Now I'm going to have 2 potassiums and 1 sulfur. I don't like that one, so get rid of it. And that's going to make 1 potassium sulfide, 1 product. Exactly the same kind of thing happening, except now with chemicals instead of sandwiches. So instead of how many sandwiches, it's how many moles of product. And what if I had 2 moles of potassium? I'll work this one together. 2 moles of potassium, here we go, 2 moles of potassium can make 1 mole of product, so 1 mole. What if I had 1.5 moles of sulfur? Well, 1.5, this is 1 makes 1, so 1.5 would make 1.5 or 1.5 moles of product. If I put them together at the same time, I can make as many as 1 from potassium. I can make as many as 1.5 with the sulfur. Combining them then, I will run out, I will make my 1 mole of product, and then I will run out of potassium. So in other words, clear that, the amount of product is limited by the reactant that runs out first. And that is what we mean by a limiting reagent. So it's kind of like a limiting reactant, except the word that we use instead of reactant is reagent. But that's really all there is to it in terms of a difference. So let's start with a bigger, slightly different reaction, a little bit bigger. Although in some ways, this reaction is going to be a little bit simpler, because you'll notice that 1 reacts with 1 to make 1 and 1. Okay, we'll clear that out. Question is, how many moles of sodium chloride? So here's the product of interest. Would be formed, how much can I make from 3.5 moles of hydrogen chloride and 2.5 moles of sodium hydroxide? You'll notice that it's not asking me anything about water. This reaction says 1 makes 1. So 3.5 could potentially make 3.5. But, clear it again, 1 makes 1, so 2.5 could only make 2.5. So I have the capacity to make 3.5 from this reactant, but I only have the capacity of making 2.5 from my second reactant. In other words, this is the reactant that's limiting. So this is the reactant, sodium hydroxide, that controls the amount of sodium chloride that I make. All right, here's where we're going to start working toward a full-scale limiting reagent question. This one will not be a full scale, but it's going to include the important parts, and then we'll layer it up after that. So here's a reaction, here's the question. Now normally, in a limiting reagent question, you're going to be working with masses, just like a stoichiometry question. Your job will be basically three things. Figure out two things, I guess. Figure out which reagent is limiting, and then figure out how much product you can make. Like a stoichiometry question, you will only have to work with one of the products, right? So you'll have two reactants. You'll figure out which one is important, which one is limiting, focus on it, and use it to find the other thing. Okay. The first job is to find out which reagent is limiting. Okay, so it's going to be exactly the same reaction in a minute. Here's how we do it. This, when you look at it, seems a little bit like a bit of a magic trick, and I don't want to say it that way because there is no magic. Mathematically, it works. We're not going to get into how it works, but it works. And all it does is let us know which reagent is limiting. So here's the same reaction. Here's the number of moles that I started with of the iron 3 oxide, 5.3 moles. I'm going to divide it by the balancing number. The balancing number there is 1, so I'll divide by 1. You don't need to do that for real, though. The other one was 15.5, and the balancing number is 3, so I divide it by 3. So now what I have is 5.3 moles and 5.17 moles. The smaller number is a limiting reagent. Easy. All there is to it. And take that out of the way. So the smaller number there is limiting reagent. As soon as I know what the limiting reagent is, that's the one I focus on. I don't have to worry about this one at all. I've got lots of it. Okay, so it's not going to be an issue. The next part of the question is, how much product could you produce? So going back to the question and the reaction, I know this is the limiting reagent, and I know I'm forming, or I'm making, I'm trying to figure out how much of the iron. So I can ignore this, and I can ignore that. Obviously, like stoichiometry, they're both there. They were just ignored for the purposes of this question. You'll also notice we have to go back to the original number of moles. So that divide by 3 and stuff that we did with the carbon monoxide, we cannot use that in the calculation for product. That was strictly for limiting reagent, determining which one was limiting. So now it's the molar ratio. So I can make 2 moles of iron, balancing coefficients, from 3 moles of carbon monoxide. So then how many would I make if I had 15.5? So that's our middle step of stoichiometry. That works out to be 10.3 moles of iron. And if all we're doing is moles and moles, we're done. But let's layer it up. So here's a new reaction. And this is going to be a full-scale limiting reagent question. This is the kind of thing that we're going to be seeing. The most important part, though, is what we just got finished doing, figuring out which one is limiting. After that, it's just stoichiometry. So job 1, calculate number of moles of each. We can't work with masses right away. We have to work with numbers of moles. Then determining the limiting reagent, and that will involve dividing by the balancing numbers. And again, for this part of the question, all I'm looking at is the reactant side. Then, once you know the limiting reagent, you use stoichiometry with that limiting reagent to figure out the mass of the product. Okay, got the steps, moving on. And we're just going to take the same reaction and we're going to work this question through. So 15.8 is coming back, 8.4 is coming back. So there's our reactant side. I don't have to worry about the product side right now. Reactant side. I'm going to calculate the number of moles of each. That's what we've been doing for a long time. That's our triangle back here, right? Number of moles is mass divided by molar mass. So take my mass, divide by the molar mass. Molar mass of aluminum chloride is 133.4. Divide that, I get 0.118 moles. Do the same thing for magnesium oxide, and I get decimal 208. Now, it shouldn't surprise us that I've got more moles of magnesium oxide because the reaction says I need more moles. It doesn't tell us yet which one is limiting. I still have to do the next step where I divide both by their balancing coefficient. And that's the next step. So the number that I had calculated in the previous part, the number that I calculated in the previous part, divide this one by 2, this one by 3, divide by the balancing coefficients. And I get 0.59 rather, and decimal 0.69. Now, quick little by the way, there are no units on these numbers, right? Most of your numerical answers need units. These are exceptions because the moles are canceling each time. This number only tells us which one is limiting, and it's the smaller one. Okay, carrying that forward, because now I can look at, here's my reactant, what does that mean for product? So my next step is stoichiometry with that limiting reagent. We know that 15.8 grams of aluminum chloride is limiting, so our next step is to use that in stoichiometry. Again, I'm not going to insist that you use this method of stoichiometry, the factor label method. That's all I'm going to be using though. It is longer and doesn't fit on the line quite as well, but it overall is going to end up taking up less space. So my original mass, grams of aluminum chloride, convert that to moles. So I've got mass of known to moles of known. So moles go on top, mass on the bottom. So the grams of aluminum chloride cancel the grams of aluminum chloride. Second step, moles of known to moles of unknown. And I just spotted a mistake. AlCl3. So moles of aluminum chloride cancel with moles of aluminum chloride. And then lastly, convert moles of aluminum oxide to mass of aluminum oxide. So these moles cancel with those moles, leaving me with grams of aluminum oxide. So when I solve that out, I have 6.04 grams. And within rounding rules, I mean, you could have a slightly different number, and we're still okay. I'm going to leave you with a question to try. We'll start class either taking that one up or having a look at it or answering any questions that you have. But here's the reaction. Here's the masses. Now again, here's my target. But before I can worry about it, I have to figure out which one of these is limiting. So I've got two masses, 53 grams and 185 grams. And at first glance, I cannot know for sure which one is limiting, so I have to calculate moles of each. So I need molar mass of ammonia, molar mass of oxygen, divide by the balancing coefficients, 4 and 7. Smaller number is limiting. Then, once I know what's limiting, I do the stoichiometry. And the stoichiometry is exactly the same kind of stoichiometry we've been doing over and over and over. And hopefully at this point, stoichiometry has become that fairly simple but tedious affair. Because at that point, all we have to do is adjust it slightly, and we still know what we're doing. Anyway, we'll be seeing you in class. Take care. Enjoy this limiting reagent stuff as much as one can enjoy stoichiometry. Talk to you later.